Hi, everybody. We're going to finish up a couple of topics related to absorption, and one of those is the effect of things like temperature, salinity, and co-solvents on the value of KOC. So we remember that we came up with our value of KOC by dividing KD by FOC. And another way of writing that same thing is to say that KOC, the equilibrium constant for absorption of a chemical between organic carbon and water, is the concentration of the chemical in the organic carbon divided by the concentration of the chemical in the water. So for most of the organic chemicals that we're talking about, KOC is pretty high. They're quite hydrophobic. They have high values of KOC. And what that's telling us is that the organic carbon fraction is the lower energy state. It's where the chemical wants to be. Whereas the CW, the aqueous phase, is a higher energy state. It takes energy to push that chemical into the aqueous phase. So as the temperature goes up, that means that more energy is available to push the chemical into the CW, into the aqueous phase. So as CW goes up, KOC must go down. Okay, so that can be very confusing. We're used to things like Henry's law constant and vapor pressure going up with temperature, but KOC is actually going to go down as temperature goes up. Now the effect is not big because KOC is quite similar to KOW, and temperature didn't have a huge effect on KOW. But we can imagine that we can write an equation similar to the equations that we've seen before, where we convert the KOC at one temperature to the KOC at another temperature by using an equation like this. And what we need to know is the delta H for moving of the chemical between the water and the particular organic matter, which we're calling POM. And we can also imagine that the value of this delta H POM to water would be equal to the excess enthalpy to dissolve the chemical in the particular organic matter minus the excess enthalpy to dissolve the chemical in water. So this is quite similar to what we saw with KOW. So what are the values of these three things? Well, we already know that for most organic chemicals, this HEW term is pretty small. For very polar and very hydrogen bonding compounds, sometimes this is even negative by 20 or 30 kilojoules per mole. And for very large nonpolar compounds like PCBs and dioxins, this can be positive by 20 or 30 kilojoules per mole. And we can imagine that the energy required to dissolve the chemical in the particular organic matter is quite low, right? Because it's, generally we're dealing with nonpolar chemicals that are happy to be in the nonpolar organic matter. Now we know in this case that the particular organic matter is quite heterogeneous. It's got a lot of different types of sites, different types of organic matter. So this would just be the average excess enthalpy to absorb the chemical onto various different types of sites or matrices. And we also know from the absorption lecture that sometimes absorption isotherms are nonlinear, which means that the value of this delta H term depends on the concentration. For absorption into a three-dimensional matrix, it turns out that we can assume that this delta H term is pretty small, and that these types of absorption processes are pretty much insensitive to temperature. For adsorption onto a 2D surface, for very hydrogen bonding compounds, that could be quite a favorable process. So this could be negative by 40 or 50 kilojoules per mole. But again, you have to remember that for these very polar hydrogen bonding compounds, the HEW was already negative by 20 or 30 kilojoules per mole. So when you subtract one from the other, you're still talking about a pretty small change with respect to temperature. So these two processes, adsorption and absorption, are both relatively insensitive to temperature, quite similar to what we saw with KOW. And if we talked about how you could estimate an HEW term, and we talked about with KOW that you might just assume that this is zero. So same rules apply here for thinking about absorption of organic chemicals to natural organic matter. We can also think about the effect of salinity on the KOC. Just like for KOW, the salinity squeezes the chemical out of the aqueous phase and therefore into the organic carbon phase. So KOC in the presence of salt should go up a little bit with respect to KOC with no salt, and we would again use the Sashnow constant multiplied by the molar salt concentration to quantify that effect. This again is assuming that the salinity has no effect on the organic carbon itself. That's a reasonable assumption as long as that organic carbon stays stuck on a particle. Later on, we're going to talk about dissolved organic carbon, and salinity will have a more complicated effect there. And again, we can talk about the effect of co-solvents, and we could make the assumption that the co-solvents would affect only the aqueous side of the equation. It would not affect the particulate organic carbon. And if we did that, we could use the same kind of equation we've seen many times before over here to describe the change in the activity coefficient and therefore on the solubility of the chemical in the presence of some volume fraction of co-solvent as being equal to the original activity coefficient for the compound dissolved in just pure water times 10 to this thing which has to do with the volume fraction of co-solvent and the slope term which depends both on the solute and the solvent. So we could use a similar kind of equation here to do KOC in the presence of some solvent is equal to the original KOC multiplied by, again, this correction term. This is where it gets a little dicey, though, because it relies on us making this assumption that the co-solvent has no effect on the organic carbon, and that may or may not be true. So if we do need to account for that, we could put a little correction factor in here, this alpha term, just to account for the fact that maybe the organic co-solvent is having some influence on the properties of the organic matter itself. But for the most part, we correct for temperature, salinity, and co-solvents. For KOC, we correct just the same way we did for KOW.